Right, just before we start today's lecture, I want to draw your attention to this. I know Neil sent an email earlier in the week announcing this too, but just in case you haven't checked your emails or checked Moodle, be aware that any announcement that was made earlier in the week regarding tutorials being held in the Earth Science Lab, you can ignore that. Okay, your practical times or tutorial times and venues remain the same as was announced in the timetable, the official timetable, USP timetable for ES106. So there will be no changes in times or locations for your tutorials. If anyone has any questions, don't ask me, ask Neil. Alright, today we're going to look at geological time. So over the past couple of lectures we've seen the structure of the Earth's internal dynamo, the activities within the various layers from the solid core to the liquid outer core and the mantle and the asthenosphere, crust at the very top. Today we're going to focus on how the planet has developed and evolved over time. So geological time. Now this is really very much a brief introduction, because this is going to again be a theme that runs through the entire course. You're looking at geology, and the farther back in time you go, the older rocks are. And that is what the topic is, looking at geology, looking at earth science, looking at the development of the planet. So three things we'll focus on. Firstly, geological time, just a brief introduction and background on it. The time periods that are involved in geological time. Some of them can be difficult to get your head around. Eons, eras, periods, epochs. From billions of years to hundreds of thousands of years. So the history of the planet concerns a lot of different aspects of development that have been continually occurring. So remember back to the idea of uniformitarianism. Everything that is happening today on the planet has always been happening in the past and will continue to happen into the future. And almost every aspect of science has contributed to our understanding of the history of the planet. We'll finish today by looking at a number of important events in the history of the Earth. So a lot of information has been gathered by studying rocks. And we'll see the detail that has emerged in terms of different scientific methods that have been developed in this class, but you will go into far more detail in these methods in the coming weeks and months. So geological time can also be considered or thought of as being deep time. The planet is 4.54 billion years old. 4.54 billion years old. And John McPhee, this guy here, is a writer, very much fascinated and interested in geology and geologists, and he said that geologists look into deep time just as astronomers look into deep space. So people who are concerned with the planets and the stars, etc., are constantly building more complex probes, more complex microscopes or telescopes to look in more detail into what's happening in deep space. The same thing is happening with geologists. They're constantly developing more accurate dating techniques to identify when exactly something happened deep in the past, deep time. So an overview firstly of geological time. Our species, Homo sapiens, appeared about 200,000 years ago. A dot at the end of this very, very long time frame. 4.54 billion years, or 4.54 billion years, or 4,500 million years, the planet formed. So we know the transitions that have occurred, the changes in terms of rock types, and the changes in terms of fossils, mammals, animals, vegetation that has occurred throughout the history of the planet by analyzing rocks, studying remains of organisms that have been left behind. And this has been continually done for the past couple of hundred years. And as I said, the more and more we study rocks, and the more time and effort and development of technology that is put into this study, the more information and the more accurate our results will be. So we have two types of ages in terms of geology. The first of these are relative ages. So we know the order of events, but not the dates in which they occurred. So before we had access to reliable radiometric dating and chemical analysis techniques that we will see in a few slides' time, all we could do was say, we knew this thing happened before this thing. So it was relative. Something happened after another event that had occurred a number of years previous. So we had timelines, but we had no exact dates. So for example, we know that World War II occurred before Fiji achieved its independence. Well, one is relative to the other, but we don't have two exact dates in this case. Benga Island is older than Kandavu, we know it, but in this case we don't have exact dates to explain the difference. So these are two examples of the approach that was taken in early geological studies. Something is older than something else. Something is younger than something else. No exact dates. Everything is relative. But as we move through time and our methods of analyzing changes in rocks, changes in chemical composition, allow us to achieve absolute dates. So we know exactly when World War II occurred, 1939 to 1945, Fiji independence in 1970. So now it's absolute. It's not relative. Average age of Benga's volcanics is 4.1 million years. Average age of Kandavu volcanics, 2 million years. So we know exactly how old Benga is in comparison to Kandavu. You can still say that Benga is older than Kandavu, but now we know how older it is. We combine these early studies with scientific advancements to obtain and achieve definitive dates, exact dates. And we'll see one method used to analyze rocks to tell us exactly how old they are. So studying the chemical makeup of rocks can allow us to tell everyone how old a certain rock is. We'll see that later on today. So a couple of ways in which information is put across to you, and these will constantly pop up throughout the course. So just be aware of them. KYRS, or KY, thousands of years in duration. So it's a length of time whenever you see this. KYRS, or KY, is a time frame, a length of time. KA on its own, thousands of years. So it's an absolute date. It's an age. KYRS, KY is a duration, time period. Ka is thousands of years of absolute date, thousands of years before present. Same for M, Y, or S, millions of years, a duration, and A, millions of years before present, an absolute age. G, Y, or S, billions of years, duration, GA, billions of years, absolute age. GA, billions of years before present, MA, millions of years before present, KA, thousands of years before present. So exact dates, absolute dates. So when we think of relative ages, the law of superposition comes into play. So this relative dating, it was the method of dating that was first undertaken or used by geologists. And if you think about it, it makes sense. So the further down into the ground you dig, the further back in time we're going to see. The oldest material is going to be deep down, the youngest material at the top. Similar with sedimentary rock. Sediments layered down at the bottom of oceans over millions of years. The oldest sediments are at the bottom, the youngest are at the top. They get compacted over time and become sedimentary rock. So the oldest is at the bottom. Girls, please. Thank you. The oldest is at the bottom, the youngest material at the top. So the principle of superposition in an undisturbed sedimentary sequence, like you have on the right-hand side here, the rocks at the bottom were deposited first, and the depositional ages decrease towards the top of the pile. Yeah, it makes sense. The bottom is the oldest. As you get towards the top, it's younger. So anything that we find within these layers then, if it's deep down, we know that it's older in comparison to anything that is higher up. So we have a relative age. A fossil found 20 meters down here in this sedimentary rock is younger in comparison to one that is 90 meters deep. A relative age, this law of superposition. In any undisturbed sedimentary sequence, the rocks at the bottom were deposited first, and as you get towards the top, the depositional age decreases. So a little bit of detective work for you using this law of superposition. So we'll say last night someone broke into the museum here in Suva and stole one of the major exhibits. The only clues that were left behind were footprints in the mud. So the thief, we know, was the last person to leave the building. And we have a number of clues. Firstly, the nephew has a guide dog. The maid drives a car, the cook rides a motorcycle, the handyman rides a bike, and the butler walks to work. So we come along and we take a photograph of the distribution of methods of movement of each of these people. So the last person to leave the premises stole the exhibit. The butler walks. Handyman rides a bike. The cook is on a motorbike. The maid drives a car, and the nephew has a guide dog. So look at the layers that are there. Which one is at the very bottom? Which one is overlain by every other method of movement? Which? The maid. Yeah. The maid who drives a car. Okay, two parallel lines with the same pattern, the tire tracks. That's at the bottom. So it couldn't possibly have been the maid, it's the oldest one. And as you work your way up through the different layers, who's at the top? Which is the newest? The nephew, exactly. So the nephew and his guide dog stole the exhibit. So this is what geologists do. You use this law of superposition. Whatever is at the bottom is the oldest, and as you work your way up, it slowly gets newer and newer until at the very top, the nephew and the guide dog steal the exhibit. So this is the type of thing that you will be doing in earth science courses. Not solving crimes, but looking at layers of deposition of rock over millions of years. Okay, good. So here you have an image of the Grand Canyon. And it is an excellent example of showing us the different layers that exist. In our last class, I mentioned that this was a very slow process. It took millions of years, I think 2.4 million years, for the material at the bottom of the Grand Canyon to be covered by the material at the top. So it's 2.4 million years old at the bottom, a couple of 2.4 billion years old, a couple of 100 million at the top. So we're looking at these layers of sedimentary rocks, and you can see the layers very clearly. Over time, they're being deposited, built up, with the youngest at the top and the oldest at the very bottom. So again, thinking of this law of superposition, the deeper and deeper you travel into the Grand Canyon, you're moving into older and older rocks. So anything that is at the bottom of the Grand Canyon in the rocks was deposited there about 2.4 billion years ago versus a couple of 100 million years at the very surface. So some relative ages then in terms of faunal succession, so animals, organisms. Fossils, the remains of ancient plants and animals, evidence of ancient life, deposited in these layers within sedimentary rocks. So the rock is a record showing how life has changed throughout time, throughout billions of years, how different organisms have appeared, evolved, died out, become extinct, been replaced by other organisms who have appeared and evolved, died out, and become extinct. And from the bottom to the top, you're moving closer to the current day. So as one group of organisms disappears from the fossil record, it's replaced by a new set of fossils. And in this case, the same form is never exactly duplicated. There's never completely exactly the same set of fossils deposited 20, 30, 40, 50 meters down. It changes as you move down or up. So what this does, it allows us to put a chronological time frame in terms of the order of appearance of different types of organisms. So they leave these fossils behind, be they plants or animals. They become fossils, they become part of the rock structure, and the farther down you go, the older these organisms are, with the youngest at the top. Yeah? All makes sense. So this idea, our examination of faunal succession, has very much come from geological records preserved in the United States, in Western Europe, and much of Asia. So lots of work being put into the analysis of fossils that are trapped and have been recorded in the various layers of sedimentary rocks throughout the planet. But when we get a situation like this, where you can have two different outcrops sticking out of the ground, but they are very, very far apart, and there are no exposed rocks in between them. And people come along and they analyze the layers that are within this outcrop of rock. So the limestone and the shale can be correlated by the fossils they contain. So the same type of fossils are contained in the limestone on one outcrop and the limestone on another outcrop, when the same fossils are within the shale in one part of the outcrop and the shale in another part of the outcrop. So it is using evidence like this that people first put forward the idea of continental drift, tectonic plates moving, dragging entire continents apart. So there's evidence of fossilized fern plants in South America, Madagascar, and southern Africa, parts of Australia, parts of the Antarctic. The same plants fossilized in rocks in continents thousands of kilometers apart, which show that, well, at one time in the past they must have been connected. So that this type of analysis, looking at fossils and their layers of distribution and the history that they've been recording, show us that areas must have been connected at one point in time in the past. So this is known as correlation. Similarity of fossils suggests similar ages, even in different rocks that are very much widely separated in space. So moving on then from relative age to absolute age, and the method that we use to understand exact dates of the ages of rocks. And this is known as radiometric dating. So within rocks there is a certain amount of radioactive material in all rocks. And we know how long it takes for this radioactive material to decay, to disappear, or change form. So it's unstable when it's exposed to the air, and it breaks down over time and it changes crystals within certain elements from one form into another. These rates of decay are constant. They will always be the same, and we'll look at an example in the next slide. So no matter where in the world you are, the rates of decay of this radioactive material will be constant. It will always stay the same. So we know that when a rock forms, there is a certain amount of radioactive material within it. And it halves over a certain number of years. So for example, potassium-argon dating. Potassium, within rocks, we know that it takes 1.3 billion years for half of it to decay. So the half-life of potassium is 1.3 billion years. So it's potassium-40, it's radioactive, it's unstable. When it's exposed to the air, the rock has been formed. It takes 1.3 billion years of it for half of it to decay and change into argon, a different element. So we can measure the relative amounts of argon in comparison to potassium-40 in minerals to determine their age. So every 1.3 billion years, the amount of potassium-40 halves. So this rock created a number of years ago, and 1.3 billion years later, half of it has decayed. So within this rock, 50% is potassium, 50% of it is argon. The concentrations of both of them are exactly the same, which tells us that it's 1.3 billion years old. Another 1.3 billion years later, there is half as much potassium-40 again. So analysing the concentrations of the two, 25% of the makeup of potassium and argon is potassium. 40 or 75% of it is argon, which means that we know that this rock must be 2.6 billion years. And another 1.3 billion years again, it's halved again, so it's about 12.5%. Another 1.3 billion years, halved again. Just over 6% of the concentrations in this rock is potassium-40. The remainder, 93 point whatever percent, is argon. So we know that this rock must be 5.2 billion years old. So it halves every 1.3 billion years. But it will never run out. It will continue to half and half and half and half for billions of years. It can be an absolutely tiny fraction of a percentage, but it will still exist within the rock. So this method, analysing potassium argon, is very useful for analysing the dates or figuring out the ages of the very old rocks that exist. Now, it takes 1.3 billion years for half of it to decay. If the rock is younger than 1.3 billion years, it's not a good approach to dating it. So instead, we can use other elements, other radioactive material within rocks, if these rocks are younger, so they have shorter half-lives. 1.3 billion years for potassium-40 to degrade into argon. There are other elements that will degrade in a much shorter time frame. So obviously dating of rocks is going to be a very important part of the course, and you will come back to get this again and again throughout the remainder of GS106. So moving on then to geological timescales. The study of fossils in the context of 4,500 million years of geological time has allowed us to produce the timeline that we have on the right-hand side. So any changes in fossils, types of organisms that have existed have allowed us to divide up the various time frames that have existed over the history of the planet. 4,500 million years of Earth history recorded in rocks. So if we know the age of a rock using our previous method, absolute dating, half-life of chemicals, we know a lot of information about how old this rock is and how old the material trapped within it is. So the best approach is to combine various methods that exist. Chemical analysis in absolute dating. You can use records of sunlight in absolute dating. Sun exposed on rock changes things within the rock, but then combine those approaches with our relative dating, whereby whatever is deeper down is older, whatever is further up is younger, and we produce this detailed geological timescale. So the Earth is 4.54 billion years old. The very bottom on this side. So I know that these notes are available on Moodle, quite difficult to make out here, so it's in your best interest to get them to see the detail in this timescale table that is on the right-hand side. So 4.54 billion years old. Within this extremely long time period, it has been divided up into eons. We have 2 eons, eras, a number of different eras, periods, and epochs. So as you move from eons, eras, periods, epochs, the time is getting shorter and shorter. So firstly, eons. And the first eon is at the bottom, Phanerozoic, Greek for visible life. So for the first maybe 700 million years of the planet, it was completely inhospitable. Too hot for anything to exist. So we had the initial creation of Earth, and we saw in our last class how the heaviest material finally sunk to the center, became solid. Our iron and nickel at the core, and surrounding that you have the liquid outer core, our mantle and our crust at the very skin at the outside. It took about 700 million years for this to happen, for it to settle, and for conditions to allow life to exist. So Phanerozoic era, visible life. For the first time we see evidence of life existing in geological record. So most life is recorded from this era, right? So from the most recent time period. Go further back in time, nothing could exist. We had lots of activity. It was too hot. The atmosphere was too poisonous. Organisms could not survive. So actually, the Precambrian then is down at the bottom. That's a super eon. There are very few fossils found in this time period. Again, because it was so inhospitable. Too hot, poisonous atmosphere. Very little exists from the Precambrian super eon. And during this time we have subdivisions: the Hadean, the Archean, Proterozoic eons. So within the Precambrian division at the bottom. So Phanerozoic, Greek for visible life. This is where fossils have been identified. They have changed in concentrations and types throughout the years. Precambrian, too inhospitable for life to exist at this point in time. So moving in one step, we're away from the eon into eras. And at the moment, we're in Cenozoic era. Cenozoic, Ceno relating to new, Cenozoic, new life. And during this Cenozoic era, extending from about 65 million years ago up to the present day, most of the fossils that we are finding are very similar to what is walking the earth today, or is growing as vegetation today. So mammals have dominated, and eventually humans came to dominate during this Cenozoic era. Meso then, Mesozoic, middle, Meso, in the middle here. Some fossils do look like what we have today, but the vast majority of them are very different. So completely different plant life, completely different bird life, animal life existing during the Mesozoic period. At this point in time, reptiles really dominated the organisms that existed on Earth. So at the moment, it's mammals. Before us, it was reptiles. The Paleozoic era in the blue here, ancient life. Paleo is ancient. Anything that is being found here, or the vast majority of fossils from the Paleozoic era, do not resemble the types of organisms that exist on Earth today. So there have been huge changes in the types of plants and mammals and reptiles and animals that existed during the Paleozoic era and Cenozoic era today. During this time, there was a change, there was this evolution, development, and a rise in the number of fish, types of amphibians, and land plants that existed on Earth. Precambrian period takes up 85% of Earth history. So of all of these developments of life forms from the Paleozoic era into the Mesozoic, into the Cenozoic today, is 15% of the history of the Earth. 85% comes in the Precambrian time frame. So everything, the vast majority of fossils that we find, the dramatic changes in the types of organisms that we find, have all occurred in 15% of the Earth's history. Very few fossils that we find come from the Precambrian period. So 85% of the history of the Earth, there's very little evidence for any life contained within fossil records. Periods and epochs then moving into the middle. Eras further divided into periods, epochs. Periods are further divided into epochs. So we are currently in the Holocene. And the Holocene began about 11,700 years ago, which is marked by the end of the last ice age. So the last ice age ended about 11,700 years ago. Since then, we've been in the Holocene. At the moment, it could be considered the Anthropocene. So anthro, anything relating to humans. So now, today, we have a huge impact on the environment. So it could be considered that today, the planet is in the Anthropocene. It could be a different development or a different epoch from the Holocene. Holocene, 11,700 years ago before, up to today, potentially today, it could be considered the Anthropocene. So we know, looking at the origin of our geosystems here, the Earth and the other planets formed about 4.6 billion years ago, and there was intense condensation of dust cloud around a very young sun. Look at this again in later classes. So the sun formed initially, and dust gathered around the sun, and this dust began to gather up, forming rocks. Over a long time period, they bombarded each other, they collided, they got bigger and bigger, and eventually we get the structure that we have today, the Earth, and all the other planets. The Earth and the other planets formed about 4.6 billion years ago, this intense condensation of dust evolving around the sun, eventually combining into larger and larger condensations to produce the Earth and all other planets. Within a few 100 million years, it's what we spoke about in our last class, the core had formed. The denser elements sank to the center, dominated by nickel and iron. So this is known as gravitational differentiation. Differentiation, differences occurring as a result of gravity, sucking and drawing the heavier, denser material towards the center of the planet. So our solid inner core, our liquid outer core, the not solid mantle, or the solid mantle, it's not a liquid, and eventually the crust on the outside. The core forms as denser elements sink to the center. Again, within a few 100 million years, the moon had formed. The moon was created as a result of the impact, it is believed, of another planet into the Earth. So Earth was spinning around the sun, it was sitting upright in its axis, and another impact or another planet came and impacted into Earth. Hit the planet, it tilted it on its axis. So today the planet spins at 23 90-degree angle because of this impact from another planet. And if another planet impacts against us, obviously it's going to create a lot of debris. So huge amounts of debris drawn away from us, the Earth, and it begins to orbit it. So the gravitational pull of Earth made sure that the debris that was created did not get sucked out into space. It remained in orbit around the planet. And over time, it collided and got bigger and bigger, eventually forming the Moon. So we're pretty sure that this was the case because rock that has been brought back from the Moon has almost the exact characteristics as rock that exists on the surface of Earth. So if they're almost exactly the same, chances are they originated together. So the planet would have been slightly bigger, Earth would have been bigger, it was impacted upon by another planet, so much debris was created that over time it collided to create the Moon and remains in orbit around the planet to this day. So during the early history of Earth, obviously, if another planet impacted into us, we would have been bombarded by lots of meteorites and asteroids and other planets hitting into us because there was chaos in space at this time. So much debris existing up there that they had not formed their usual orbits around the sun. It was too early in the creation of the universe at this point. So today we have lost the evidence of these impacts and these craters because of plate tectonics and weathering. Two things that change the face and the surface of the planet. But if you look at the Moon and you can see with the naked eye even, not even using a telescope, you can see lots of craters, impact of other material recorded on the surface of the Moon. How come it's still there and not on Earth? There is no weathering on the Moon. There is no plate tectonics on the Moon. So there are records of all of the impacts and craters that have been created on the surface of the Moon, but here on Earth we've lost the majority of these impacts and craters because of weathering and because of plate tectonics. So we know that the oldest mineral on Earth exists from 4.4 billion years ago. So the planet is about 4.54 billion years. Girls, once more and you can leave. So it took 100 million years or more for the first minerals to form because it was too hot for them to solidify before that. So there are rocks in Jack's Hill in Australia contain zircon, a mineral that we know is 4.4 billion years old. 3.8 billion years ago, rocks began to show evidence of running water. So ripples appearing on the surface, erosion being recorded. 3.8 billion years ago, we know that the hydrosphere had started to form. There was water flowing on the surface. 3.5 billion years ago, thinking back to our last class, the geodynamo, the magnetic field that exists within the planet because of the actions of the core and the liquid outer core. We have evidence from 3.5 billion years ago of magnetic fields. 2.5 billion years ago, large continents have begun to develop. Oceans and the atmosphere continue to form during this time period through degassing. So water begins to be recorded. We have initial evidence of a hydrosphere, of flowing water. Where did it come from? The vast majority of it probably through degassing of volcanoes, releasing water vapor into the atmosphere. So for the first couple of billion years, it was too hot. Any water vapor that was released into the atmosphere could not condense into droplets. But over time, as the planet cooled down, water was allowed to form. So if it was forming in the atmosphere, it formed clouds, it fell as rain. It's also possible for water to have been introduced from asteroids. They're very much dominated by ice. Eventually, life moderated the atmosphere, where the first single-celled organisms, such as cyanobacteria, algae, etc., began breathing in the carbon dioxide in the atmosphere and releasing oxygen. And over billions of years of these tiny organisms taking carbon dioxide out of the atmosphere, adding oxygen, more complex organisms were allowed to occur. They developed and evolved over time. Until today, you have 21% of the air that we breathe is oxygen, which is perfect for us to survive. Sometime earlier than 650 million years ago, it's thought that the entire planet was either completely or almost completely covered by ice. 650 million years ago, we know that there is evidence for glacial deposits even in the tropics. Material that is only left behind and the pattern of deposits that is only done by the actions of glaciers. Evidence of this even occurring in the tropics 650 million years ago. So sediments deposited by glaciers right the way throughout the planet. We're not entirely sure how this occurred. How did it get so cold that the entire planet essentially became a snowball? Might have been caused by an increase in the atmosphere from oxygen from photosynthesizers. It reacts with methane, it reduces the greenhouse effect, and suddenly it becomes intensely cold. So this forms an interesting debate. How can it happen? It's debated amongst scientists. How can the entire planet suddenly freeze? And also, how can we get out of this situation where the entire planet was frozen over? So it's something that's vital in our understanding of long-term climate change and long-term geological change. We don't have an answer. 3.5 billion years ago, the first primitive bacteria evolved and developed. 2.7 billion years onwards, rise of oxygen concentrations in the atmosphere, as I mentioned, most likely as a result of cyanobacteria breathing in carbon dioxide, poisonous carbon dioxide, and releasing oxygen. Same way that plants and trees do today. 2.1 billion years ago, seaweeds and algae begin to evolve. So our life forms are getting more complicated because there's less poison in the atmosphere. There's more oxygen in the atmosphere. 542 million years ago, we have what is known as the Cambrian explosion. And during this time frame, about 30 million years, there was a huge, huge increase in the diversity of organisms that suddenly appeared on Earth. So from about 542 million years ago to 515 million years ago, we had the appearance of things like jellyfish, other worms and organisms, vertebrates, snails, etc. suddenly appeared on Earth. And often they were quite bizarre creatures. Evidence from Burgess shale fossils in British Columbia and Canada for this creature here. 2 meters long. Anomalocaris. Into the ocean, existed in the oceans. Again, fossils recorded in shale, in British Columbia, in Canada, of creatures that we would only dream of in nightmares today, maybe. So in this situation, this Burgess shale fossil, it's about 540 million years old. And there are some extremely detailed fossils recorded within it. And in some instances, the tissue of these organisms still exists. So maybe we'll have some sort of a Jurassic Park type situation in the future where these guys suddenly start swimming in the ocean again. Not likely. Actually, don't mention to Eleanor I said that after what I said about the core the other day. Ignore those scientific movies. 600 million years ago, we have the first animals. 540 million years ago, we had that Cambrian explosion. 443 million years ago, we have the first mass extinction of life. So something occurred where a huge amount of organisms suddenly died out. And we know this by looking at the fossil record. Analyzing organisms from 444 million years ago to 442 million years ago, there is a distinct difference between the fossils that exist. 420 million years ago, first land mammals. A number of mass extinctions, 359, 251, and 200 million years ago. Again, huge differences between the types of fossils, plants and animals, from one layer to the next layer. 125 million years ago, our first flowering plants. 65 million years ago, one that you all probably know of, another mass extinction, and the last mass extinction that the planet encountered. So here you have the death of about half of all species on Earth, including the dinosaurs. Quite possibly as a result of the impact of a meteorite in and around modern-day Mexico. So it threw so much dust into the atmosphere that it changed global climate. 5 million years ago, first appearance of hominids, our early ancestors. 200,000 years ago, appearance of Homo sapiens, so us. So during the extinction 251 million years ago, 95% of all species went extinct. 95% of everything that existed before this time frame disappeared. It's likely that this is as a result of intense volcanic activity persisting for a number of years, completely changing the climate of the planet, blocking out the rays of the sun, dropping temperatures, causing the vast majority of organisms to die. So if you consider the planet and the history of the planet as a 24-hour clock, humans appeared at 11:58 and 43 seconds. 1 minute, just over 1¼ minutes to midnight. This is how long we have been on the planet. Everything else has occurred in the preceding 11 and 58 minutes, hours. All right, so we are only here for a fraction of a time frame. Okay, we will leave it at that for today.